Okay, for this week, in the last module, we will discuss implicit function theorem and its application. So, implicit function theorem, one can say, is the so far whatever we have done is just we try to lift whatever we had from function of one variable to function of several variables, and for that we needed to develop certain techniques, certain technical issues we have to deal with. But as far as the implicit function theorem and its applications are concerned, this is typically a statement in several variable, and one can say this is one of first non-trivial theorem what one encounters in differential calculus dealing with functions of several variable, and it is often confusing. The statement often seems to be confusing if it is written in a, if you see a book and just try to turn the pages to find implicit function theorem, it is from the first reading or even the second reading, it is very difficult to understand what is going on. So, I try to do it in a very simple fashion, and I will do it in detail for function of two variables, and you will see that from function of two variables to generalize it function of any variables taking values in any Rm, this is just mere formalities. So, what is the idea here? The idea or the question, basic question begins here. That suppose I have a nice function of one variable, nice means let us say smooth enough, defined on some interval to R. Now, given a function, first one tries to plot it, right. So, here is my interval a b, and one tries to plot a nice function g out there. So, what it means, for each value of x, I have a g x over here. Now, if I look at this curve, this is a curve in R2, right. This is a curve in R2. So, points on the curves are basically x g x. So, this point is x g x, x in a b, and all of you know that such a thing is called the graph of g, and we have been doing it for the first moment we introduce function, we have been drawing graphs of function. This is graph of a function g, and if g is nice smooth, then this graph will be nice in the sense that I can draw transient to this curve, I can draw normal. So, a function gives rise to a graph of a curve in R2, which is the graph of the function. Now, suppose on the other hand, I just give you a curve in R2. How do I say it is a curve in R2? Well, this is, I say that is okay, do not look at, I do not know any function of one variable or saying exist or not, but I say this is a curve which is governed by this rule, that any points on this curve x y satisfy this relation f of x y equal to constant for some x f. For example, So, I have a function f from some interval u to r, u in R2, sorry, some open set or some set u in R2 and f from u to r, and look at all those points f x y equal to c. So, which is called a level curve, that I have a function f and I look at all those x y such that f of x y is constant, and I call that is a curve, level curve of f. For example, just take a simple example. Suppose I define this function f from R2 to R, very simple one, f of x y, let us say x plus y. This is a function of two variables taking value in R. And I look at this line, a line is a curve, which is, I say this curve is nothing but, you can look at f x y equal to, let us say 1. So, line x plus, this is a line x plus y equal to 1, and so if you look at the function f of x y equal to x plus y, this is the level curve of this function. And the question is, given a level curve in R2, we can ask this same question in R3 when I given level surface. So, R3 it will be a surface. So, if I look at in f from R3 to R, then f x y z equal to constant, this will be some surface in R3. So, now I can ask this question for a curve that okay fine, I have a nice level curve, f is nice enough in whatever sense. Is it a graph of a function, that do I have a function g like that actually this level curve f x y equal to c comes from the graph of a function g? Well, or for the surface, can I ask this question that does there exist a function g from let us say R2 to R such that R2. So, can I write f x y equal to c, this set, that set of all x y here, this is as same as x belong to some interval a b. Can I do this? Or here f x y z equal to c, can I write it as some set x y g x y g from some set in R2 to R. So, the question is the level curve is a graph? Well, if you look at this example, this f x y equal to 1, this you can easily see this is actually set of all point x and y equal to 1 minus x, x in R. So, this is graph of the function, graph of g, where g is from R to R and g of x equal to 1 minus x. So, instead of saying f x y equal to 1, if I give you this set of point x 1 minus x or x g x going to R, you will get the same curve. Seems very nice that this curve we can write as graph of a function, but a simple thought, if extended little bit, you will see that this answer may be negative as well, because suppose I look at this function. This is a very nice function, x square plus y square, and I look at the level curve. All of you know, if I plot it, what I will get a circle of radius 1 in R2. Now, if I want to write it, now the question, if I ask this question now, can I have a function g defined on some interval such that I can write this curve, any point on the curve as x g x? No matter how you try, you will not be able to do it, right? Because whatever x you choose x here. If I have a function, this value will be g x, but corresponding to this point x, there are 2 y. Similarly, other way around, corresponding to any y here, there are 2 x's. So, neither as function of x or not as a function of y. I cannot write. I need at least 2 functions here. So, need at least 2 functions to write it as graph, namely g x equal to 1 is positive square root, which will give you this part, and another is negative square root, which will give you this part. So, this level curve is actually union of x g 1 x, x in R, and x g x g 2 x, x in R, and these two union are not disjoint, or are they? Oh yeah, they are not disjoint. When x equal to 1, then y is 0, right? Yeah, x equal to 1 or minus 1, y is 0. So, it is not a disjoint union. So, even for this simple level curve, which is very nice, it has tangent everything, but I cannot write it as a graph of a function. But one thing is sure, that if I want to look at a portion of this curve, let us say this portion of course I can write as a function. So, this I can of course write as graph of g2. This portion also I can write graph of g2 in some proper interval x y here also. So, this gives us that maybe we should not be asking this question for the entire curve. So, we should be asking the question. So, let me form the question now in full generality, that suppose I have a function fn f from Rm to Rm, and I look at a generalized level surface f of x equal to some, okay, let us say some y naught x in Rn, and y naught is a fixed vector in Rn. The question is, can I write it as graph of a function that is does there exist a G from R n minus m. So, here my n is bigger than m to R m such that this set of point x y f of x y equal to y naught x in R m R n minus m y is in R m equal to x g x for some g in some interval theta in R n minus m to R m. So, this is the question written in full generality. So, in particular for R2 to R, I ask the question, does there exist a function of one variable such that this is a graph of a function. So, question formulated very in layman's term is every level curve or surface is a graph. Answer is no, as I said. So, I should what I should do, as I showed the answer is no. So, the question should not be this, because if I do it the answer is no. So, now we should add one term here. Can I write it locally as a graph of a function? That is, does there exist this? So, that is given x naught y naught in the curve such that f of x naught equal to y naught, does there exist a neighborhood of x dot y naught and g from R n minus m to R m such that in that neighborhood f inverse. So, in that neighborhood, let us say, does there exist a neighborhood, let us give it a name U, in that neighborhood U, f inverse of y naught intersection U is the graph of this function. There is a confusion because this y naught, maybe I should change it to some constant, right, some c. C is a fixed vector in R m. So, f inverse of c is this. So, this is the question, and of course, implicit function theorem says the answer is yes, that is it. But it is a very useful theorem in calculus, and as I said, I will illustrate it for curves in R2 to R, and then tell you how to do it for any general, to answer this question in generality. So, where is the question now? So, I look at f of x y equal to, let's instead of C, let's take 0, it does not matter, right. I can also take C, consume in F. So, what I am looking for? So given, so x naught y naught is such a point. Looking for a neighborhood of x naught y naught, let us say of the form, let us say of the form some x minus epsilon 1 x plus epsilon 1 cross x naught y naught minus epsilon 2 y naught plus epsilon 2 such that there exist G defined on x naught minus epsilon 1 to x naught plus epsilon 1 to R and if x y belongs to this neighborhood, then f inverse of 0 intersection this neighborhood. Okay, let us say instead of writing it and of course, I should have G of x naught equal to y naught because it must be satisfied. So, does there exist such a G? So, this question simplified from for a curve is this one. So, try to understand the statement first, question first, then we will see how we will get that. Okay? Statement clear, I guess. Otherwise, rewind your video and see it again. Well, I do not want to state the implicit function theorem straight away. Before anything else, let us see if I want to achieve such a thing, what we need. So, we will form the statement from whatever information we gather. So, what we need to define such a D? Let us see one by one. This should be a function, right. So, in that neighborhood, so I need to decide a neighborhood first U I need G as a function here and this level curve is a graph. So, what I need that? I need to decide a neighborhood U such that for each x there exist, this is the part where G is a function, there exist unique y, right, such that f of x y equal to 0. If there is no unique y, I cannot define G. So, that was the problem here for the circle. Given this x, any x here, there were 2 y. Okay. So, I have to decide, but now I am asking this question locally. So, I will not look at the entire curve. So, I will look at, let us say, this portion of the curve only. Okay. I will treat this as this part of the curve as my local level surface, and here I can decide a neighborhood. Of course, I can take here entire thing, it is a very nice picture, such that for each x there is only y. So, when I am asking this question, I am not looking at this part, I am looking at this part only. So, that is what is meant by looking at locally. Okay. So, how do you do that? So, how to achieve 1? To achieve 1, one may go like this, that so fix x in x naught minus epsilon to x naught plus epsilon 1 and consider y going to f x y. What I need? I need an interval y naught minus epsilon 2, y naught plus epsilon 2, where this function has a unique 0, right. That is what I have translated this part. Now, how do you get a unique 0? First of all, I need a 0. So, I need a 0 means, so continuous function having 0. So, if I do something like this, suppose f x at y naught minus epsilon 2 and f x at y naught plus epsilon 2, they have different sign, then one is positive, one is negative, then there will be by continuity there will be 1 0. But I need unique 0, and how do I use? So, this will give a 0. How do I get a unique 0? Well, if I ensure that f of x y is strictly increasing or decreasing in then the 0 will be unique, there cannot be more than 1. So, this is the second reduction we will need. So, we will continue from here in the next lecture.